Okay, let me do more practice to improve my oral English. Today I want to introduce this paper towards understanding the generative capability of adversarially robust classifiers. This paper is published in ICCV 2021 and it's accepted as an oral paper, and so it should be excellent. But yeah, of course, I can only give you a very brief introduction. I cannot cover some important uh, concepts or content in the paper, which will make it really simple. So maybe it's not why it gets an oral, right? The authors are from Zhejiang University and the Huawei Noyes Arc Lab. Summary. This paper, in fact, is just combined two concepts. One is FGSM. It's for we know is for the adversarial examples and the adversarial training from Young Goodfellow. Yeah. And another concept is the GEM, Joint Energy-Based Model. This paper, the paper title is your classifier is secretly an energy-based model and you should treat it as one. A very long name. So the framework we can see here is it's mainly the first term we can see it's just the cross entropy to train a standard softmax classifiers. And the second term log likelihood p of x it's the it will use the energy-based model training. Maybe you are not familiar with this one, so you should be familiar with this one. Then you can know what they did. And what is changed in their paper is that the first you can see this pseudocode. They will generate adversarial examples, but here is the energy-based ones, not the traditional ones. Traditional you should know it based on this one. Gradient is the loss of x and y between x, y, and times the budgets epsilon, then plus 2 original x. So I hope it's the traditional one. You should know it, but now it's change it. Very simple, in fact. So you can see what they did is just okay. Here they add some random noise, and this is the gradient. And the main difference is this part. The gradient, the loss will be different. Here it's used. The loss is namely the probability, predicted probability of the ground truth of y of this category. Now it's use the logits value, the logit value of the y of that category. So you should know that one. It's from extract an h, then it's go to the final classifier, final fully connect layer to get the z, and use the softmax to get the probability. So they use this z. The softmax, you know, it's epsilon of the z divided by the summation of all the values here. So now they don't use this one. They just directly consider the this value. But of course you should notice it's add or subtract, it's negative or positive. Usually the direction you should be careful. But the main idea is here. They use zy instead of this loss, the p of y given x, to compute the x adversarial examples. Then this part is very general for energy-based model training. Use the SGRD, stochastic gradient Langevin dynamics. I will it, uh, ignore this part. Then they update the model parameters. So you can see this one, in fact, it's also the cross entropy item, cross entropy item. So in fact, because they write it in the uh, energy form, in the energy form, in fact, it's just log p of y given x. And now they change the x. Previously, they used the real x from the real data. Now they use the adversarial examples from to replace the real x data. Also for this term, both use x adv. Adv here is also adv. Okay, and so they have these two terms, and the thing add together to update the model's parameter. So the idea is very simple. They just consider uh, these modifications, and the benefits I cannot cover in this slide in this lecture because yeah it's a paper. First, they found this one is better than the uh, previous one. They only this one is they don't consider this part, and they use this x z y to compute the adversarial example. Then it's better than previous robust classifier using PGD. Then for the final one, they add the log p x with the x adv. Then they show that the flatness is much better than previous methods. But mhm. But other content I cannot cover that. Okay, they define true matrix for their method because if you only compare the first, let's see the accuracy. You can see on the cif the standard accuracy it drops a lot, maybe not a lot, but it's very common uh, when they use the adversarial examples. Uh, like the PGD method, it will drop like 10% from the standard classifier. Now you can see here it drops about, let me see, 8 points, 8%, 8% from the gem. And they improved the robustness. Maybe it's good, but yeah, the trade-off still happens. And the data set, in fact, it's data sets they use are very simple. They only consider cif The maybe they have cif 100, but uh, maybe in the appendix, I didn't check it very carefully. So if it's from a university lab, a college lab, maybe it's good, maybe it's okay, but yeah, it's a company, right? They are doing internship in the Huawei's Huawei as a company, and that I think they should have much stronger computation resource. Why they can only run on cif and cif 100 for some stronger if they have more. Yeah, never mind. I hope they can run on better, stronger data sets. And let's go back. Okay, so you can see the accuracy drops and the image quality here. The generated images quality inception score and FID, especially FID. Here is the typo. The less the less the better. Their typo, not mine, not mine. Right? So you can see their method is just almost the same as the previous gem, and the inception score, it's very flat. It's not stable. Its final epoch can, uh, how to say, changes very dramatically. So we can we can see it's just comparable. So the total uh, generative image quality are close. So they define another true true new matrix to show their method are much better, are much better. But let's check the definition. So we can see this one they called joint FS, and this one marginal FS. The performance they show is much better than previous method. However, that's if we take care look at the definition carefully, we can see this one is just use the x, the joint f x and y. This one is only x, so we let's consider one. Okay, yeah, we only need to check one. Now we can see for this one how to, yeah, they didn't give a really accurate definition, especially they didn't open source their code. Then how can they, how they, how do they compute this one? I'm not sure. First, this one we know for this single value, then take gradient over the x, it should be a matrix, right? Matrix, a value take gradient over x 1 0 0, and this value gradient over this x n1 1n 1n nn. So and this one, the L2 norm or the full or something, I forgot the name. The L2 norm is summation through the line and the column, and every value a. Okay, yeah, what a square and take square and here square again. So it's just the uh, the the summation of all elements square. Summation of the square of all elements is the summation of all the take take square take square every element, then take the summation. I think it's the definition of this one. Okay, and for this one, how they compute it is also an interesting problem. So again, for this one, first ignore this one is also a matrix, right? Then take gradient, take square. The power 2 square is two. Yeah, every number, right? Then they use the trace. How they compute the trace on this matrix? Why they compute the trace? If they only compute the trace, then it's the definition of the trace of a square matrix is defined this one. It's the summation of belong the diagonal, right? Diagonal I 1 1 2 2 n. So it's the summation of diagonal, which mainly represents the summation of this number. So the difference between these two items is the summation of the remaining items. They don't they subtract the diagonals. And why do they measure this one? This only means every element on other pixels almost almost zero. Other elements almost zero. I think they can even consider the whole matrix, because if it's for a mesh x, right? Take the gradient of x, then the gradient, the diagonal of image uh, doesn't represent anything. And if they still if they consider it as yeah, how they define this, how they really define this trace, I still think it's a problem. I cannot get the idea of it. I cannot get the idea of it. Yeah. What does it mean? Yeah, if it's the x, the gradient of x, the maybe 28 times 28, the diagonal don't indicate anything. But if it's a matrix of the 3 times 32 times 32, and the rows 3 times 32 times 32. How, how they computed this matrix? I yeah, yeah, that's really strange, a strange definition. Hmm. Okay, so yeah, no code, so I cannot really understand it. Okay, that's my problem. Let's go. Yeah, I just have some very simple consideration. Yeah, because for this one, the drop from the uh, gen or from the standard classifier through the adversarial training model. Then we know this paper published in CVPR. They have an auxiliary batch norm. Use it, it can improve the accuracy when they use the adversarial examples as data augmentation. However, this paper it, it only applies on ImageNet, even not consider CIFAR10 and CIFAR 100. And what if they use they didn't use it for data augmentation method? Then what it will happen? It will be yeah, that's a very hard problem, because they have tried this one, but they only consider the data augmentation case and the only ImageNet case. If you try on CIFAR10, CIFAR 100, and uh, it's you cannot say you propose a new method, but uh, but maybe you can try it for this one to on this. Maybe we can try it on this one. Very simple, but for fun. Yeah, for fun. Okay. Yeah. Thanks.